Right, so this third example is the last type of example that you'll get. So this one's a little bit different because what we're doing is mixing some weak acid with some strong base. And then what happens is we know that this weak acid, so methanoic acid, will react with the strong base in just a normal neutralization reaction. So we're going to get this sodium methanoate and some water. So what we know is that this is going to be the source of your methanoate ion. So that's your conjugate base. Some of this will be left over, so that's your weak acid. All of this will be used. So whenever we do this kind of process for making buffers, you always need more moles of your weak acid than you have moles of your strong base. Otherwise, all of your acid will be used up and you won't be left with anything of any use. So the first thing we need to do in the calculation, so we're trying to calculate the pH, is work out how many moles of our conjugate base and how many moles of our weak acid are left over. So we'll do this one first, work out how many is reacted. We know that the methanoic acid is in excess, so at the moment that is not useful to us. We need to use the volume and concentration of the sodium hydroxide. So volume is 10 centimeter cubed, so 0.1 decimeters cubed. Concentration is 1, so our number of moles is 0.01 moles of sodium hydroxide. Now that's important because obviously we have a 1-to-1 ratio here, which means that we have produced 0.01 moles of our sodium ethanoate. So that's important. We can also then use that, so we also know, because we have a 1-to-1 ratio here, we also know that 0.01 moles of the methanoic acid has reacted. Now that's not really telling us anything yet because we need to know how many moles we started off with. So initially we can say that we had 0.025 decimeters cubed, so that's the volume, multiplied by the concentration, 0.5, gives us, so to begin with, we started with 0.0125 moles of our methanoic acid. Now we also know that 0.01 have been used, so we take away the 0.01 that reacted, and that will give us 0.0025 moles of our weak acid, methanoic acid, left over. So that's what's in your buffer solution. So we need these number of moles. So we've got, remember, the 0.01 moles is our conjugate base, and then we've got the 0.025 moles is our weak acid. Those two numbers actually need to be concentrations before we can put them into our hydrogen ion calculation. So we need to divide each of those number of moles by our total volume. So 25 plus 10 gives us 35 centimeters cubed. So for HA, concentration of HA moles, 0.0025 divided by the total volume, 0.035 decimeters cubed. So that equals 0.0714-ish, and the concentration of our conjugate base, remember again, it's actually this, but we're saying there's 100% dissociation, so this number also is the number of moles of conjugate base, so 0.01 over our volume, 35 centimeters cubed, equals 0.285, blah, blah, blah. So those concentrations can then be put into the same formula or arrangement that we've seen before. So you can start learning this now. So hydrogen ions equal Ka multiplied by HA over A minus. So we've seen how that's derived already. You can derive it each time if you want to, or you can just remember it. So Ka, given in the question, 1.78 times 10 to the minus 4, multiplied by the concentration of HA over the concentration of A minus. Type all of that in, and we get 1.78 times 10 to the minus 4 times 0.074. We get 4.459 times 10 to the minus 5. And obviously then what we want to do is calculate the pH. So as we've seen many times before, minus log of your hydrogen ion concentration, in this case, will give us 4.35. And that's it.